All right, guys, today we are going to go over calorimetry. Calorimetry is a way that we can measure the enthalpy of a reaction, or the delta H, in a lab. So when we say the delta H of the reaction, what we're really talking about is the amount of heat that is either absorbed or released from the reaction. Now, the problem is that we can't measure heat directly. So we are going to use something called a calorimeter in order to collect the data that we need. Once we have all of that data, we can use that to find the amount of energy that is either released by the reaction or absorbed by the reaction. The very simplest calorimeter is just a styrofoam cup. So you want something that is very, very insulated. And then in that insulated object, you can run your reaction. When we run the reaction, we are going to keep track of two different parts. First, there is the water. Second, there is the reaction. Now, remember that energy cannot be created or destroyed, so any energy that is released from the reaction would be absorbed by the water. Since it can't be created or destroyed, it has to be the exact same amount of energy. Likewise, if a reaction is endothermic and absorbing energy, the exact same amount of energy has to be released by the water. So we essentially have two components to a calorimeter. We have the reaction and we have the water around it. In this example, we're going to work through how to use calorimeter data in order to calculate the delta H for the reaction. The reaction we are going to look at today involves two chemicals, H2SO4 as our first reactant and NaOH as our second reactant. First thing we need to do is write a balanced equation to show the reaction between the two. All right, my balanced equation is written below. I have NaOH reacting with H2SO4 to produce H2O and Na2SO4. Our overall goal here is to determine the delta H of this reaction, and we would like that answer to be in kilojoules per mole. Whenever I'm starting any problem in chemistry, I like to list everything I know underneath the substance that it refers to. We're often given a ton of numbers and a ton of data, so let's start out by focusing on the amounts of NaOH and H2SO4. All right, so from the information given, I know that I'm starting with NaOH, and I have 0.15 molarity and 25 milliliters. This 25 milliliters is not super helpful. Liters is far more useful, so I'm going to divide that by 1,000 in order to get 0.025 liters. Then I'm also starting with a 0.1 molar solution of H2SO4 and 50 milliliters of that. So I need to divide my 50 milliliters by 1,000 in order to get 0.05 liters. Now, notice that I know the amounts of both of my reactants. Thinking back to our stoichiometry, this means that we are going to need to determine the limiting reactant. The limiting reactant is really important when we are dealing with thermochemistry because the limiting reactant is the reactant that runs out first. As soon as we run out of it, we stop making product, but we also stop absorbing or releasing energy. So we need to figure out which is the limiting reactant. The limiting reactant will always dictate the amount of energy absorbed or released. There are several ways to determine the limiting reactant. If you have a way that works for you, that is totally fine. The way that I typically suggest to find the limiting reactant is to use your starting materials and figure out how much product you're going to produce. We know that the limiting reactant will always produce the lesser amount of product. So I'm going to first start with NaOH, and I'm going to calculate how much water I can make. In a second problem, I am then going to start with the H2SO4 and determine how much water I can make. Whichever one makes the lesser amount of water is going to be our limiting reactant. Because I know the molarity and I know the liters, I can use my equation molarity equals moles over liters to determine how many moles of NaOH I am starting with in this reaction. I'm then going to convert my moles of NaOH to moles of H2O using the 2:2 ratio in the balanced equation. If I use all of the NaOH here, and I fully consume it in the reaction, I know that I will produce 0.00375 moles of water. I'm now going to do a second problem and see how much of the water I can make if I use all of the H2SO4. Once again, I know the molarity and I know the liters of the H2SO4. If I know molarity and liters, I can find moles using the equation molarity equals moles over liters. When I do that, I find that I started with 0.005 moles of H2SO4. I can then use the ratio from the balanced equation to determine how many moles of water I will make if I use all of the H2SO4. Now I have two different answers. but both of them are in moles of water. That means I can directly compare them. And because the 0.00375 is the smaller amount, I know that's the amount of water I can produce. Now, really, I don't care how much product I can make. What I care about is the limiting reactant. And from the math that I have here, I know that NaOH is the limiting. That means that all of the math that I do in this problem in relation to thermochemistry is going to have to do with the NaOH. Since that is going to run out first, that is going to determine how much energy is either absorbed or released throughout the course of the reaction. All right, now that I've determined my limiting reactant is the NaOH, now I'm ready to start in on calculating the amount of heat. It's important to remember that energy cannot be created or destroyed in a reaction. So when we are talking in terms of energy, the Q of the reaction that occurs between NaOH and H2SO4 plus the Q of the solution around the reaction has to equal 0. Energy cannot be created or destroyed. Now, the problem is that I cannot measure the NaOH and H2SO4 reaction directly. So I can't stick a thermometer in and measure the temperature change of the NaOH and H2SO4 on its own individually. But I can measure the Q of the solution around the reaction. So that solution around the reaction is water-based because our solutions are water-based. So we can find the Q of the solution using the equation Q equals mc delta T. In this equation, we know that Q is heat in joules, m is our mass, C is our specific heat capacity, and delta T is our change in temperature. We are now ready to start the reaction. In order to do so, we are going to dump the NaOH solution into the calorimeter with the H2SO4. As we mix it, we're going to see that the temperature of the water around the solution is going to change. In this case, it is going up to 20.7 degrees Celsius. I listed all of the variables that we need to know about the solution. Notice that I broke the delta T into initial and final, and I can always get the change in temperature by taking the final minus the initial. So let's start with the mass. We can assume that the density of water is 1, and because the density of water is 1, 50 milliliters is equivalent to 50 grams. So I had 50 grams of water in the first solution, and when I added the second solution in, that was an additional 25 milliliters of water, which was an additional 25 grams. So in the calorimeter, at the end, I have 75 grams of solution. Even though we've added some solute in here and the reaction has occurred, unless we are told otherwise, we are going to assume that the specific heat capacity of the solution is the same as the specific heat capacity of water, 4.184. The temperature when we first started, before any reaction occurred, was 20 degrees Celsius, and after we mixed the two solutions, the final temperature rose to 20.7 degrees Celsius. I now have all of the variables except for Q. I'm going to plug my variables into my equation. My mass is 75, my specific heat capacity is 4.184, and notice that I took my final minus my initial temperature of 0.7 degrees Celsius. It's important to always take the final minus the initial because remember that your temperature change could be negative, so you have to be careful to always take the final minus the initial. This gives me a Q value of 219.66 joules. But remember that this is the Q of the solution, or the water around the reaction. So I know that this came out a positive number, which means that the water, or the solution, absorbed energy. Well, all of the energy that it absorbed to raise the temperature, that 0.7 degrees, had to have come from the reaction itself. So that means that if the Q of the solution is positive 219, the Q of the reaction is equal to negative 219.66 joules. Again, the Q of the reaction and the Q of the solution will always add up to 0. So now I know the Q of the reaction. I know how much energy was given off when we mixed the H2SO4 and the NaOH. But remember that our end goal here is to get the delta H of the reaction, and that needs to be reported in kilojoules per mole. Right now, I have joules, not kilojoules, so let's address that problem first. I can get from joules to kilojoules by simply dividing by 1,000. When I do that, I get 0.2197 kilojoules. That is the number of kilojoules that was released from this reaction. But remember that I did not use a full mole in this reaction. If you remember back to our original calculations, I knew that NaOH was my limiting reactant. So my NaOH ran out first in this reaction, and I know that I used 0.00375 moles of that NaOH. Now, I would like to scale those kilojoules up so that it's kilojoules per 1 full mole. There's a couple of ways to do this, but if you are a ratio person, 0.02197 kilojoules is to 0.00375 moles, as some amount of kilojoules is to 1 mole. You can simply do cross multiplication here in order to solve, and we find that our answer is negative 58.6 kilojoules. This is per mole of NaOH. Now, when you're done, you always want to go back and check your balanced equation. This delta H of the reaction should reflect the balanced equation that you have here. So if we want this to reflect the balanced equation, we have to remember that this balanced equation shows us 2 moles of NaOH. So we are going to need to multiply this value by 2 in order to reflect the 2 in front of the NaOH. If we did all of our calculations based on the H2SO4, if that was the limiting, then we would not need to scale it up because there's only a 1 there, so we wouldn't have to double it. When I double it, I get negative 117 kilojoules. So we are going to put that in as our final answer. Negative 117 kilojoules per mole based on the balanced equation that is there. Because that carries a negative sign, we know that this reaction is exothermic. So the reaction between the H2SO4 and NaOH released energy, and that energy was absorbed by the water, thus the temperature change or increase in temperature in the water. All right, let's take a look at a second problem. In this second problem, we are going to solve for something just a little bit different. This time, we are going to use the exact same reaction that we did before, the NaOH and the H2SO4. Notice I have my balanced equation here. And this time, we already know the delta H of the reaction. We figured that out in the last problem. It's negative 117 kilojoules per mole, meaning that the reaction is exothermic and releasing energy. All right, this problem is telling us that we have a 2.2 gram sample of NaOH and it's mixed with 200 milliliters of 0.1 molar H2SO4 in a calorimeter. The initial temperature of the solution is 22 degrees and it wants us to find the final temperature of that solution. Remember that the amount of energy absorbed or released in a reaction is dependent on the limiting reactant. Whichever reactant runs out first will also cause the reaction to stop absorbing or releasing energy. So since we know the amounts of both reactants, we are going to have to start by determining which is the limiting. Again, there's more than one way to do this, but I'm going to model this by starting with one reactant, determining how much product it can make, and then using the other reactant and determine how much of that same product it can make. Whichever makes the lesser amount will be our limiting reactant. Let's get started. I know I'm starting with 2.2 grams of NaOH. First thing I need to do is convert that into moles. I do that by adding up its molar mass on the periodic table. And I know that there are 40 grams in 1 mole of NaOH. Now, it doesn't matter which product I choose to go to, as long as I go to the same product for both of my problems in determining the limiting. So I'm just going to choose H2O since that's the first one listed. For every 2 moles of NaOH, I get 2 moles of H2O according to the coefficients in the balanced equation. If I use all 2.2 grams of NaOH, I know that I will make 0.055 moles of water, but it's possible that the H2SO4 could run out first. So let's check to see if H2SO4 is the limiting. For the H2SO4, I am given milliliters and molarity. Since it's a solution, I'm going to need to use my molarity equation, which is molarity equals moles over liters. I'm going to plug in the 0.1 for my molarity, and rather than using 200 milliliters, I need to be sure to convert that to liters and divide by 1,000, giving me 0.2 liters. I'm going to plug that in, which allows me to solve for X. When I solve for X, I find that I have 0.02 moles of H2SO4. I can then convert that to product using the ratio in the balanced equation. For every 1 mole of H2SO4, I know that I am going to produce 2 moles of water. All right, so if I use all of the H2SO4, I will only produce 0.04 moles of H2O. Remember that the smaller answer is always the correct one, because as soon as one reactant or ingredient runs out, the entire reaction stops. So since this is the lower amount, I know that the starting material that produced that, the H2SO4, is the limiting. Now that I've determined that the H2SO4 is the limiting reactant, I know that the amount of energy that is released during this reaction is going to be dependent on the amount of H2SO4 that was put into the reaction. As soon as we run out of H2SO4, we stop producing energy. I have now determined that H2SO4 is my limiting reactant, so now it's time to start to work on the calorimetry piece. This is where I'm going to do my heat calculations. Remember, just like in the last problem, that the Q, or the heat of the reaction, plus the Q of the solution around it is going to be equal to 0. Again, energy cannot be created or destroyed, so all energy absorbed by one substance must be released by another. I can't find the Q of the reaction directly, but I can measure the Q of the solution in my calorimeter. The Q is equal to mc delta T, so I'm going to list all of my variables. Again, I'm going to break my delta T, or my change in temperature, down to initial and final temperature. Remember, the end goal here is to find the final temperature of the solution. I know that the initial temperature from the problem is 22 degrees Celsius, and my solution is water-based, so we can assume that the specific heat capacity is 4.184 joules per gram degrees Celsius, unless it states otherwise. Now, as far as the mass is concerned, this problem is a little bit different than the problem that we did before, because we don't have two solutions. When we had two solutions, we just took our milliliters of solution and assumed that since it was water-based, the density was 1, which allowed us to use grams instead of milliliters. But now I have 200 milliliters of solution. That is still equivalent to 200 grams. But my NaOH is a solid, and that is not in solution. So that is a 2.2 gram sample. So when I'm talking about the Q of the solution, I'm going to add the mass of the solution and the mass of the solid to give me the mass of the entire solution at 202.2 grams. Notice that I still don't know the Q of the solution. I also am missing the final temperature. I can't use my equation until I have 4 out of the 5 variables. So if my end goal is to get the final temperature, I'm going to need to find a way to get the Q of the solution. Remember that there's a relationship between the Q of the solution and the Q of the reaction. When I add them together, they always add up to 0. Well, this time, I know the delta H of the reaction. The delta H of the reaction is 117 kilojoules per mole. But remember, I did not use a full mole of anything in this problem. I started with 2.2 grams of NaOH and 200 milliliters of a 0.1 molar H2SO4 solution. So I know from my first calculation that H2SO4 is the limiting reactant here. Looking back at this, I can see that I put 0.02 moles of H2SO4, the limiting reactant, into this reaction. I am going to need that to help me figure out how much energy was absorbed when the 0.02 moles of H2SO4 reacted. It's important that you always start with your limiting reactants. I can find the Q of the reaction because I know that I started with 0.02 moles of H2SO4, and that was my limiting reactant. If that's the amount that I put into the calorimeter, then I can figure out how much energy that 0.02 moles would release. According to my equation here, I know that for every 1 mole, according to my balanced equation, of H2SO4, I am going to release 117 kilojoules of energy. Rather than leaving this in kilojoules, I am going to convert it to joules because I know that my specific heat value over here is in joules as well. So rather than staying in kilojoules, I'm going to convert it to joules. I know that there are 1,000 joules in 1 kilojoule. When I do the math here, I know that from the 0.02 moles of H2SO4 that I put in the calorimeter, I will release 2,340 joules. That is the Q value of the reaction. But remember that the Q of the reaction plus the Q of the solution equals 0. That means that the amount of energy absorbed by the solution will be the exact same quantity, just opposite in sign. I now know that the Q of the solution, or the amount of energy that the solution absorbed, must be 2,340. Since I know the Q of the solution, as well as the mass of the solution, the specific heat of the solution, and the initial temperature of the solution, I can now use my Q equals mc delta T equation in order to solve for the final temperature. All right, I can now sub in my numbers. So instead of Q, I put 2340. Notice that it is positive because this is in relation to the Q of the solution. For the mass, 202.2, my specific heat capacity, and then instead of delta T, I always need to take my final minus my initial. Since I don't know my final, I'm going to call my final x and minus 22. All right, I'm going to solve for x by simplifying. I can combine these two terms to get 846 times x minus 22. Divide both sides by 846. I can reduce that down to 2.77 equals x minus 22. I can then solve for x. That gives me a final temperature of 24.77 degrees. This makes sense. If the reaction released energy, I know that the temperature of the water should go up as a result, since the water or solution around it is absorbing that energy. So my temperature did indeed go from 22 to 24.77. I hope that helped with calorimetry and how to find the enthalpy of the reaction. Don't forget to check out my other videos, and thanks for watching.